Okay, so what if we have slightly more complex systems, ones where we perhaps don't have just 3 atoms in a row, but we may have 4 or 6 and so on? We can still generate good MO pictures for these. Now, this one I would expect you to do fully, and this one there are parts of it that I would expect you to do, but I wouldn't necessarily expect you to be able to generate all of them. So let's start with the part I definitely want you to be able to do. I want you to be able to identify how many p orbitals exist in a row in these systems. How big is the system that we're talking about? And I'd also like you to be able to generate how many electrons are in the pi system. So how many extended p orbitals do we have in a row? How many are linked together? For this molecule, of course, there should be 4, 1 at each carbon atom, and you can go ahead and just simply draw them in and realize that there have to be those 4, and we can build our pi system from that. There are, of course, scenarios where I could draw a molecule that had, say, a couple of pi p orbitals in a row, and then a break, and then possibly some more, and so on. So how many p orbitals linked together are in this molecule? Well, you have 2 p orbitals in a row here. That's what gives rise to the pi bond. And then this oxygen has the potential to have a p orbital that could be linked into the system. But how many in a row? Well, there's actually a break in the chain. These 2 are together, and then this one's isolated. So when I'm asking how many p orbitals are in a row, what I'm talking about is conjugated, which means really consecutive. Here we have 4 in a row. How many do we have here? Well, we have 6 all in a row. Each one of those carbon atoms contains its own p orbital. And they're all in a row, and they're all lined up with each other. Okay, so question 1, how many p orbitals in a row? Relatively straightforward. You just count how many have an extra p orbital that could potentially be lined up, and you see if there's any breaks and so on. Here we have 4, here we have 6. How many electrons are in the pi system? We have 2 double bonds here, therefore 4 electrons. 2 from that double bond, 2 from that double bond. How many pi electrons here? 6. 3 different double bonds, each of which is bringing 2 to the system. Okay, so now the key question, and the part where this molecule I expect you to be able to do, I expect you to be able to generate all 4 orbitals here. This one we're not going to worry about. Okay, so what would the 4 orbitals be? Well, you're first going to take all 4 of these and put them onto a line. So in other words, what you're going to do is draw the carbon chain as a straight line and put 4 nuclei in a row on it. And then we can start filling out the actual, each one of these orbitals will have an associated energy with it, of course. What are the shapes of the orbitals? Well, there's one more piece that I haven't talked about yet, and that is that the orbitals either have to be purely symmetrical or purely anti-symmetrical. So in other words, this lowest energy orbital here is always going to be easy. It's always going to be the one that's fully aligned. All of the p orbitals are lined up with each other. This will always be a symmetrical orbital as well. The electron is allowed to go anywhere in the system it wants, and it's the main reason why we do MO theory. There is always going to be one orbital where the electron is allowed to go freely, and it's always going to be the lowest energy. It's not going to have any nodes other than the internuclear axis. So it'll have 0 nodes in one sense. Okay, the next one that's easy to generate is always going to be the highest energy orbital, which is always going to be strictly alternating, and therefore it's going to be antisymmetric as long as you have a even number of orbitals. So in other words, this is going to be up, down, and you can see that it is antisymmetric because the right-hand side of the molecule and the left-hand side of the molecule are opposite each other, whereas this is symmetric. The right-hand side of the molecule and the left are the same. This then creates several nodes in addition to the internuclear axis. Everywhere the p orbitals alternate creates a new node. And this will always be the general finding as well. The lowest energy orbital is not going to have any nodes. The next one is going to have 1 node, the next one's going to have 2 nodes, the next one's going to have 3 nodes, and so on. This is, of course, always going to be a pi bonding orbital. This one, of course, is always going to be a pi anti-bonding orbital. And these in the middle could have some bonding character or not bonding character, depending on the details. So we had a symmetrical orbital down here, we have an anti-symmetrical orbital up there, and usually what happens is you kind of alternate between them as you go up as well. So one way that you could generate one node in an anti-symmetrical fashion is to put that node smack in the middle of the molecule, like so. Which means that the left-hand side of the molecule needs to be in alignment with each other, and the right-hand side of the molecule needs to be in alignment with each other, and they are opposite each other. So in other words, the anti-symmetrical part is the left-hand side and the right-hand side are different from each other. Okay, and then the next one up is of course going to be one where you have 2 nodes, and the easiest way to generate that is to put the 2 nodes here and then fill out the orbitals in between. And again, you're going to ensure that the orbitals that are next to each other have the same phase so that they can overlap. And then we should go ahead and fill out the electrons in the system. So we have 4 electrons, which means we're clearly going to fill the pi bonding orbital, and we're also going to fill this one. And bear in mind that the Lewis picture for this would suggest that you have 2 isolated double bonds, and that's kind of what this picture is showing. But keep in mind that the advantage to thinking about this in MO theory is there's going to be an orbital where the electrons can move freely, and then there's going to be an orbital up there that can react differently. This would be the highest occupied molecular orbital. This would be the lowest unoccupied molecular orbital. And of course, this would be an empty orbital as well. This is, in general, how you would generate the pi bonding image, the MO picture for butadiene. Before I move on to benzene, I wanted to reiterate and clarify a couple of things. The first is that when you are generating the orbitals for any system, you should start by a strictly symmetrical orbital, and then the next one up is going to be anti-symmetrical, and the next one up is going to be symmetrical and anti-symmetrical, and so on and so forth. And a lot of the details for how the pi systems will end up will depend on whether you have an odd number or an even number of p orbitals involved in the construction of the system. But the other thing I wanted to do here was to show a different way of representing the phases. So far, what I've done for the phases is to draw the actual p orbitals in question. And so what I'm highlighting here is that they are all the same phase. But another way that this is typically done is by just simply saying all of these have the same phase by drawing pluses and minuses. And therefore, if I drew them all plus, you would infer they're all the same phase. Whether that's shaded or not shaded is arbitrary. But one way of representing the lowest energy orbital of butadiene would be all pluses, all the same. Whereas the anti-symmetric orbital then would be, say, 2 pluses and 2 minuses, or 2 minuses and 2 pluses. Again, it's arbitrary. But the point is that it's anti-symmetrical. The left side and the right side are different. Then the next one up will be symmetrical, and that means that the 2 orbitals in the middle have to be the same phase as each other, but opposite the phases of the orbitals on the outside. And again, arbitrary, but you'd have to have that. And then finally, I have erred in the construction of my nodes. I have no nodes here, 1, 2, so clearly this needs to have a third node smack in the middle, and then the orbitals need to strictly alternate. The highest energy antibonding orbital is always going to be the one where the orbitals strictly alternate. And therefore what we're going to have up top would be, say, minus, plus, minus, plus. Now the key point I would like to make for everything that we're going to do in benzene is that I don't expect you to be able to generate these orbitals, because there are some complexities here, and it's simply not that important that you be able to do it. Having said that, I do think it illustrates some interesting things about nodes, therefore I want to talk about it in some sense. So the key thing to keep in mind is if you mix together 4 p orbitals, you're going to end up with 4 MOs. So here, if I'm mixing together 6 orbitals, I'm going to end up with 6 MOs. But in this cyclic system, unlike the acyclic system, some of those orbitals will end up as the same energy. In fact, the usual format for orbital energy is going to be something like this, where everywhere that you have a vertex in the benzene, you would have an energy orbital. And so what we have is the lowest energy orbital is down here, and then we have 2 orbitals that have the same energy, 2 more orbitals that have the same energy, and then 1 different orbital up there. Orbitals with the same energy are said to be degenerate, and therefore both of these orbitals are degenerate, as well as this set of orbitals above them. Okay, so the really important thing to keep in mind, of course, is that I'm going to be generating 6 orbitals, and therefore I need to have 6 diagrams here. And I'm going to be using this plus-minus sort of indication. And I'm going to go from having 0 nodes, aside from the plane of the page, which of course is where all the atoms are, but 0 nodes all the way up to the highest number of nodes. But every orbital that I generate is going to have 1 more node. So I'm going to go 0 nodes, 1 node for these 2 orbitals, 2 nodes for these 2 orbitals, 3 nodes there. And likewise, I'm going to be strictly alternating symmetrical orbital, anti-symmetrical, symmetrical orbital, anti-symmetrical. Alright, so here we go. The lowest energy orbital is always easy. Every single one of the orbitals needs to be in phase with each other.
No problems there. Okay, so the next one up has to be both anti-symmetrical and needs to have one node. And I submit to you that there's two obvious places to draw nodes in order to generate an anti-symmetrical orbital, and they are as follows. So again, this one has to be an anti-symmetrical orbital because the first one was symmetrical. Of course, this means that orbitals that are on the same side of the node as each other all need to share the same phase, and if they're on opposite sides of the node as each other, then they need to be opposite phases. And so the right way to read the orbitals, both orbitals I've just generated, is that they are bonding orbitals. These three carbon atoms are all bound to each other in the pi system. These three are bound to each other, but there is no bonding across the top and then bottom. And likewise here, these two are bound to each other. These two are bound, but this is non-bonding on this plane. So again, the lowest energy orbital is symmetrical, the next highest is anti-symmetrical. So that means the one above it has to be symmetrical as well, and it likewise has to contain two nodes. And again, the most straightforward way to generate that would be to do something rather like this, where you have two nodes that way, or alternatively, two nodes rotated, say, this way. Then everywhere you are separated by a node from another atom, you clearly have to flip the phases so it looks like that, whereas here, these two are going to be the same phase as each other, but opposite phase to the one that's across the node from each other, so it looks like so. And then, of course, finally, the highest energy orbital of all is going to have three nodes, and it's going to be strictly anti-symmetrical. And so the obvious place to draw three nodes is, of course, bisecting each of these faces of the molecule, which then, of course, leads to strictly alternating, as one would expect. Again, I don't expect you to generate this set of orbitals, and yet, the reason why I was doing it is simply to show you that you go from strictly symmetrical to strictly anti-symmetrical, alternating all the way up, and you are always increasing the nodes by one as you go to the next set of orbitals up. The exact details of how you do this for benzene are not important for this course, but fundamentally, those are the rules that we're applying. And then the last thing that I'll mention here for benzene is, of course, we're going to fill the lowest energy orbitals in turn, and we have 6 electrons to fill these orbitals, which therefore means that the highest occupied molecular orbitals are, in this case, 2 degenerate orbitals. They are the same. There's no real difference here. So these are both the highest occupied molecular orbitals, and then, of course, these are the lowest unoccupied molecular orbitals. So if you are going to react benzene with something that will accept electrons from the benzene, you would need to examine this set of orbitals to figure out how benzene would react. Whereas, if something on the outside was going to donate electron density to the benzene, you would be examining this set of orbitals to figure out how benzene would react.